Yo, guys, this is a fun but maybe crazy idea, but I'm gonna be solving a fluids problem. Fluids wasn't my favorite class in college, so kind of wanna do it outside of school without the pressure of grades and see how I like it. So, yeah, we're gonna solve a problem about a capillary tube viscometer. It's not hard. I'm gonna keep it simple and try to explain it as best as I can. So let's solve this problem. I'm gonna paste the problem in the video so you can see it, and that should be that. I'll walk you through how to solve it, and then we can move on from there. So the problem is a viscometer problem. I'm trying to make sure you could actually see this so it's focused. So it's a viscometer problem. It kind of looks like this. You're gonna see that in the video. First of all, a capillary viscometer, the kinematic viscosity of the liquid is proportional to the drain time. So the kinematic viscosity is usually used like that sign. And it's proportional, if you know the proportional time, to T. So kinematic viscosity is proportional to T, which is how long it takes the draining time. So drain time. So if you've done any sort of proportional like math before, you know, like directly proportional, you put the constant, boom. So this constant is the calibration constant. And in this problem, we have a calibration liquid. So we're gonna use that liquid to determine a liquid of known kinematic viscosity, and we're gonna find out the drain time, and then we're gonna use those two values to calibrate the viscometer, which is this device. Kinematic viscosity and dynamic viscosity, I'll explain that maybe later in the video if I have time. I'm trying to not take your time too much. Okay, so glycerine is our known liquid. So we have our viscometer. We need to know what the calibration constant is. We have glycerine, and we know that at 20 degrees Celsius, it has a kinematic viscosity of, can you see all that? At 20, yeah, it has a kinematic viscosity of 1.19 times 10 to the negative 3 meters squared per second. So we need to find out, oh, we don't need to find out the drain time. We also know the drain time. So the drain time for this is 1,430 seconds. Hopefully that looks good. Okay, so we know the kinematic viscosity and the drain time. Now, basic algebra. If we know kinematic viscosity, we don't know the calibration constant, and we know the drain time, we're looking for K. So rocket science, K is equal to what? T over V? Am I tweaking? Yeah, I am tweaking. K is equal to V over T. So forget this. I don't know how to do algebra. I'm an engineer, not a mathematician, so forgive me. Anyway, so we take 1.19 times 10 to the negative 3 meters squared per second. Use your units, they're gonna help you. So meters squared per second over second. So the calibration constant K is gonna be what? Can you see all that? Anyway, when we do all that, we should get 8.3 times 10 to the negative 7. So when we're doing this, let's do it quick. You can see my calculator. 1.19 times 10 to the negative, boom, booklet. Did I forget how to use a calculator, bro? 10 to the negative 3. That's equal to this. And then we divide it by, oh, I didn't even put this out here. I just put the seconds. So it's 1,430 seconds. So we divide that, 1430. That's the answer. It's 8.32 times 10 to the negative 7. What are the units? So we have meters squared per second squared. Because second, that's second to the negative 1. If you bring it up, second to the, it's algebra, bro. I'll freshen up. Anyway, we know what K is now. Now all we gotta do is use this K to find the kinematic viscosity of a, what's it called? Of an unknown liquid. So there's some unknown liquid, and we know we're gonna use this viscometer that I talked about up here for like an experiment. So we've done the experiment for glycerine. We know the viscosity, and we know, and then we put it through here. We see the drain time. We use that in this formula to calculate the calibration constant of the viscometer. Now we know what K is. We now get a liquid of unknown kinematic viscosity. Yeah, and we take that liquid and put it through the viscometer. When we do that, we can now what? Measure the drain time, like with a clock, right? So once we measure the drain time, we can now use this calibration constant we found and the drain time to find the kinematic viscosity of the unknown liquid, which will help us find the dynamic viscosity of the unknown liquid. So unknown liquid, what's unknown? The kinematic viscosity of the unknown liquid, we don't know what that is. The drain time of the unknown liquid is given in the question as 900 seconds. And we have found K with that. So again, not rocket science. If we take the formula is equal to KT, we're looking for what? V. So we know K and T. So K would be 8.37. Oh, nope. Don't make that mistake. 8.3 times 10 to the negative 7 meters squared per second square times 900 seconds. These, your units will help you. Hopefully my handwriting is not complete dog shit. But here, after you do that multiplication, you should get like 7.5 times 10 to the negative 4. Writing under a camera is not fun. Meters squared per second. This multiplication is the constant that we got earlier. So this constant tells us the calibration of the viscometer. And this is the drain time. So we did the experiment, we poured the unknown liquid in there, and it took 900 seconds. So by multiplying those two, because the kinematic viscosity is directly proportional to the time it takes, and we know the constant, we're able to find the kinematic viscosity of the unknown liquid. And then we could use that to find the dynamic viscosity. So dynamic viscosity is mu is equal to rho of the kinematic viscosity. So if the density of the unknown liquid is also known and is given as 970 kilogram per meter cube, we can use that here in this formula. Again, not rocket science, pretty simple algebra. So 970 kilogram per meter cube times the kinematic viscosity, which is 7.5 times 10 to the negative 4 meters squared per second. So units are going to cancel, and you should have 970 times 7.5 times 7.5 times 10 to the negative 4. So that's 0.73. This is kilogram meter square. So kilogram meter square cancels meter cube. So we have over meter second. So kilogram meter, I believe that's past. This turns out to be 0.73 Pascal second. There's a unit conversion there that I'm not going through, but hopefully this wasn't completely out of frame. So the last time I looked at the camera, it was in frame. But you see how we found the unknown viscosity, and then we use the formula for that. This is dynamic viscosity. So dynamic viscosity That's what we're looking for. That's the final question. And we found the kinematic viscosity of the unknown liquid. We know the density of the unknown liquid, and we're able to multiply that and find the kinematic viscosity. So there we go. This turned out to be 10 minutes. Sheesh.